On Monday, we learn about the performance metrics of the binary classification. In this case, we are using the confusion matrix. And if you already look at this matrix, we have the actual and the predicted. And you can know what is the true positive, true negative, and false positive and false negative. We also look at the F1 or F1 score. It is to measure the imbalance data, where the number of label data for each class should be balanced. If it is not balanced or if it is imbalanced, then we need to consider using the F1 score. And there's also another measure, which is MCC, Matthew Correlation Coefficient. We look at the testing set and we look at the training set, and we learn how to calculate the accuracy, the precision, and recall. So let's look at the code. Okay, the internet is quite slow today. Yeah, we have the data set, which is about the pay goal. And as you know, all data are categorical. When the data are categorical, you need to change this categorical data into numerical. One of the way to change the data from categorical data into numerical is to use one-hot encoding. Use get dummies. Then we can get the value 1 0 1 0 0 0 0. It means if the attribute outlook rainy is 1, then it means the outlook is rainy, and sunny is 0. If the temperature hot is 1, then it means this data or this row, the temperature is hot, and the other attribute is only 0, or that is not the true value. So like this one, play golf equals to yes. If it is 0, it means this is no. If it is 1, then it means it is true. So we can get numbers from this one, and we can split the numbers, or we can split the x and y. We know that the x are the attributes except the play golf. So the play golf, yes, is the y, or we call this is the response. The remaining attributes, they are the x. Then we just drop this column. We call this is the drop. We drop the play golf, yes, and we put into the y. So x are the attributes except play golf, and y is play golf. And then if you look at this one, then okay, I have 14 and 6, and then I have the data from the x, and I have the data from the head. So I'm doing the splitting, the training, and the testing. If you still remember, when we apply the test size 0.2, it means the training size is 0.8 or 80%, and the testing size or the testing set is 20%. So we can look at the shape, the training data. We have 11,6. It means we have 11 rows and 6 columns. For the testing, we have 3 rows and 6 columns. For the Y training, we have 11 rows and nothing. It means we have only 1 column. And the Y test, we have 3 rows and nothing. It means we have only 1 column. So this is the data for the training. You can see this is the training data. There are 11 data for the training, and we have the testing data. The testing data, we have 3 rows. And we use the KNN to look at the prediction compared to the actual result. So this is the actual result. The play golf is 110. Okay, so last time I put the value here. The actual, it is the 110. And we perform the prediction using KNN. I run the KNN. In this case, let me choose the number of neighbors, which is 3, and then fit the training data. By fitting the training data from the X and Y, we are creating a model. And after we have the model, let's look at the training data. And let's look at the testing data. So we are going to predict. After we have a model on the KNN classifier, we are going to predict the X test. The X test, it means we have the 3 rows that we have, and then do the testing. This on this X, we are going to predict with the Y. So we have this prediction. The prediction result is 1, 0, 1. So this is what I explained to you before. The prediction result is 1, 0, 1. So the actual is 1, but the prediction is 1. Okay. The actual is 1, the prediction is 0. The actual is 0 and the prediction is 1. Then you can measure the confusion matrix. This is the confusion matrix that we learned for the testing dataset. In order to perform the matrix, we can call the library. In this case, we use the accuracy score and the confusion matrix. Okay, this is the accuracy and this is the confusion matrix. This is the confusion matrix 0, 1, 1, 1. In this case, it is the opposite from this one. It is 1, 1, 1, 0. Okay. In Python, yeah, this is the true negative. This is the true positive. Okay. It is in the opposite from the lectures. And we can apply the other kind of measures. For example, the precision, recall, F1, and the Matthew correlation coefficient. We do this precision on the actual data, which is the testing Y, and then the prediction data. Testing, prediction, testing, prediction, testing, and the prediction. Then we can get the value of the testing result. We have the accuracy, which is 0.3. We have the precision, which is 0.5. We have recall, which is 0.5. We have F1, 0.5. And we have MCC, which is minus 0.5. So those are the same with this result. The accuracy is 0.333. Precision is 1 divided by 2. Recall is 1 divided by 2. And you can measure by yourself the F1 and also the MCC. Because we have the precision, we have recall, we have the true positive, true negative, false negative, and false positive. So you can just apply those into the formula. Now, we can do the other kind of performance. we can do the performance for the training data. So I'm using the training data and I'm going to predict. It means I'm checking the models. If the models we apply to the training data, what is the result? So once I have the model, I apply to the training data and I can measure the performance. So the performance will be the comparison between the training data and the prediction on the training data. This is the precision from the training data, Y, and the prediction using the training data. This is the recall using the training data and the prediction of the training data. And we can produce the confusion matrix, and this is the confusion matrix. So we can see this confusion matrix is the same with the result here. So this is the opposite. Okay, 7031. This one is 7031. You can check. This is the prediction result. 111110, 11111. Then it is 11110, 11111. If I plot this one into a plot, you can see this is the testing, this is the training. And if you look at the result, the data, okay, the training value is high, or the training accuracy. So the accuracy on the training data set is high, and the accuracy on the testing data set is low. The precision on the training data is high. The precision on the testing data is half, 50-50, and so on. Okay. Now, we can plot like this one. If you look at this data, the training performance is high, but the testing performance is low. So this is something that we need to analyze. Now, let's look at the PowerPoint again. We come to the word about overfitting. So what is the overfitting? There are three kinds of model performance that you need to check. The first is underfitting, and the other is just right. And the last one is overfitting. Underfitting. What is underfitting? It happens when your training error is high. When you have the error is high, it means the accuracy is low. Okay. When you do the error, if you still remember in the regression, like we use error. The error, if the error is near 0, then it is good. If the error is high, it is bad. The same with the accuracy. Okay. When the accuracy is high, it is good. When the accuracy is low, it is bad. Then underfitting means high training error, or we can say it is bad, or the low accuracy, it is bad. So when the result or the metric is bad, we call this is underfitting. The training error close to the test error. So when you do on the training data, the result is almost similar to the testing data. Then we call this is underfitting. We can see from this picture, from the regression, if you have this data, okay, then let's say this is the model. So the error will be very high. The error will be very high because the error means the distance between the data and the model, the distance between the data and the model, and so on. The underfitting, we can say this is high bias because this data is very far from the model. So the model itself does not represent the data. On the other hand, we have overfitting. Okay, we have the underfitting, we have overfitting. Overfitting means if the data is very good, okay, what we call this is low training error. Okay. Low training error means the error is nearby zero, okay, almost zero, and or high training accuracy. High training accuracy means the accuracy, or I say ACC, is nearby 1 or nearby 100%. And the training error much lower than the test error, or the training accuracy is much higher than the test accuracy. What does it mean? If the training error, you can see from here, if the training error, sorry, this is the training error, is much lower than the testing error. It means the performance on the training data is very good, but the performance on the testing data is very bad. So if there are a big gap between the result on the training data and the testing data, then there might be a problem of overfitting. Or if we look at the accuracy, if we look at the accuracy, the training accuracy much higher than the test accuracy. So on the training data, maybe the training accuracy is 99%, but the testing accuracy is 60%. Okay, it means when we do with the training data, it is good, but when we do the testing, it is bad. This might be overfitting. Why we need to consider this overfitting? Because if you look at this problem, the model is very good. The model can distinguish the blue and the red. So the model is very unique in this case. Okay, the model follows the instance very clear. Then it means the accuracy is very high. However, when we have a new data, the model is not good. The model is good only on the training data. Model is very good on the training data, but the model is not good on the testing data. So the testing data, when we do the testing, it is bad. Then there is a high possibility of fitting. Whenever you do the modeling, you need to get the just right. It means the training error slightly lower than the testing error. Or sometimes we can say the training accuracy slightly higher than testing accuracy. So if the gap between the training accuracy and the testing accuracy is not that big, so the model can be accepted. So the model can be the just right model. So for example, if you look at this one, the error between the training and the testing is not that big gap, then we can say this is just right model. When you do the modeling later for the regression and the classification, it is good if you can do it just right. So you need to check, like what we already learned before. You need to check on the training data and you need to check on the testing data. If the testing data and the training data has no big gap, then no problem. If the testing data and the training data has a very big gap, then you need to be very careful with the overfitting. The overfitting can be explained with this figure. Do you know pet? Chimney. Okay. Do you want to buy this kind of pet? Even chimney salvo itu? Of course not, because this is not a general one. We cannot use this kind of pet because this is only a specific for one person, maybe. So the overfitting can be explained like this one. If you have a model, the model should be able to apply in every data. So if only one data set can be applied, like for this one, then the model is bad. Okay. Or the model, maybe we call it, this is overfitting. The result, you can see here, based on the result, the training and the testing, there is a big gap. This is 0.7, this is 0.3. This is 0.7, this is 0.5. This is 1, this is 0.5. So there is a big gap between the training and the testing. So for this case, what should we do? Okay. For underfitting, if your model is underfitting, it means you need to develop feature engineering. So you need to think what is the best features for your data. Maybe the one hot encoding is not enough. One hot encoding is not enough. Maybe you need to have another features. Or you need to develop better machine learning models. Maybe in this data, KNN is not good. So you need to use another kind of algorithm. Maybe we can use decision tree. Or maybe we can use SVM. Or maybe we can use another algorithm. So you need to compare with different machine learning models. The other kind of problem is about the overfitting. If overfitting happens, you need to do regularization. So regularization means you need to check the error. Okay. So there is a kind of research on the regularization. It means you need to check the error gap. You need to minimize the error gap between the model and the testing data. Or the other kind of solution is to get more data. So the data maybe it is very small. So last time there was one team who asked me, is it okay if I have only 1,000 data for the team project? Actually, I cannot say yes or I cannot say no because it depends on the data. If you have a very small data, I'm afraid that you will have the overfitting because the data is very small. So I recommend you to have more data. Maybe, I don't know, maybe 5,000. I don't know, maybe 10,000. There is no specific number of data that is good or bad, but it depends on the data set itself or it depends on the domain. So more data is better. I will explain the same as what we learned in the regression. We can improve the performance using some of the methods that we already learned. Now let's take a look on the iris dataset. if you still remember, we have iris, we have three, this is versicolor, setosa, and virginica. So those are the variables, sepal length, sepal width, petal length, petal width. And y is this response, and the response is categorical value. If this is the features, or if these are the attributes, I know that this is setosa. With this value, I know this is setosa, and so on. Now using this data, again, we can do the machine learning. First, we need to select what is the x and what is the y. For now, because the y or the response is the flower, then I can specify the column species. Okay, the column species is y. And other than the column species is the x. So I drop the column species and then I put it as the x. Y is only the column species. When you have the data, please do the data pre-processing. For this example, because the data is good, so there is no such of data pre-processing. There is no missing value. All data are in the numerical, so we can easily do the modeling. So the units also in centimeter for all features. Sepal length, sepal width, petal width. All of them are in the centimeter. So they are in the same range. Then, yeah, there is no need to do pre-processing on the features. Now, there is something that we need to convert or transform, which is the label. The label that you saw before, it is in the categorical data, setosa, virginica, and versicolor. Then we need to change these three labels into numbers because computer cannot understand the category. Then we need to transform them into numerical. Last time you learned one method for converting the categorical into numerical. We can transform them using the label encoder. Okay, the label encoder means we are going to make the label, in this case the categorical data label, into a value. So we want to encode. Then we are going to change the y. We are going to transform y with the label encoder. Then the value of y later on, we will check the setosa will be 0. Maybe the virginica will be 2. The versicolor will be 3, something like this. Then the value will be 1, 2, and 3. And then we will do the splitting 80-20 because we have the training data and we are going to make the model with the training data. After we have the model, we are going to testing in the testing set. So let's have this one, 20 and 80. We can do the KNN. Now I'm just using the KNN, and let's suppose the n neighbors is 3. We can do the prediction. After we do the fitting, we can do the prediction. It means I'm using the X from the testing data and I will get the prediction result. Using the prediction result, I'm going to check the difference between the Y on the testing data and the Y on the prediction result and check the accuracy. Again, I can create the confusion matrix, check the Y on the testing data and check the prediction result. I can create the confusion matrix. And now, what is binary? binary means 0 and 1. So there are two options. However, in the flowers, how many flowers do we have? How many flowers? We have 3 flowers. Okay. So the 3 flowers means the flower 1, flower 2, and flower 3. So the class, there are 3 classes. Meanwhile, for the binary classification, we have 2 classes. For example, in the golf dataset, we have only 2 values, which is yes, play golf yes, or play golf no. So this is binary classification. In the iris dataset, we have 3 flowers. So we have 3 values. It means it is more than 2 values. If it is more than 2 values, then we call this is multi-class. The target is multi-class, but the default average is binary. So whenever you do with the precision score, recall score, F1 score, they have the default value for binary classification. Then you need to choose another average setting. For example, you can choose none, or you can choose micro, or you can choose macro, or you can choose weighted. If it is none, it means we do not do any average. So we just put the original value. If use micro, it means if we have 3 classes, then we will do for the class 1. We do the performance on the class 1. We do the performance on the class 2. And we do the performance on the class 3. And we show each of them. If we use macro, so we do the performance all of them at once and then show it. If we do it weighted, so we will do the performance of 1, 2, and 3, and then do the average. And for this weighted, the average will be equal for every class. So let's just do with the average weighted for the precision, recall, and F1. You can see the parameter here, the average weighted, the average weighted, and the average weighted. Okay, now let's see. So this is the one that I explained before. We use the label encoder to show the Y. Yeah, if you want to check, you can copy and paste your Jupyter notebook into your environment. Let's say here's Y. So Y has been converted into numbers. So 0, maybe this is Setosa. 1, maybe this is, I don't know, Versicolor or Virginica. And 2, yeah, the other one. So we have 3 different classes. And then we will split 80-20 and check. Okay, the training data we have 120 and the testing data we have 30. Then we do the classification with the KNN. We do the prediction and we get the matrix, the confusion matrix. If you see the confusion matrix now, the matrix become 3 multiplied by 3 because we have 3 values. I think this is Setosa. I think this is Virginica or Versicolor. Okay. You already learned the holdout method. Okay, let me review a little bit. The holdout method means we will do the proportion from the testing and the training. If you split into two distinct sets, then you have training and testing. If you split into three distinct sets, then you have training, validation, and testing. The proportion, yeah, it depends on the number of data. If you do 80-20, it is common. But if your data is too small, I think it's better to use 60-40. If the data is quite big, maybe sometimes we have 90-10. So if the data is big, means maybe you have 10 million data, 10,000,000 data. Then you can use this because it is quite good. But if your data is very small, let's say you have 1,000 data, maybe you need to use this one to make a good model. Now you can refer to the code. We can split the training, validation, and testing. Suppose we have 60-20-20. So last time we also learned on the regression. We can split the data. We have train and temp. The temp is the temporary. So let's assume that the training is 60 and the temp is 40%. Then the test size is 40%. The test size combined is 40%, and I put it into the X temp or the temporary. After I have the text X temp and X train, now I can split again into 2 or 0.5. So I'm going to split the X temp and Y temp 50-50. So 50 for the validation and another 50% for the testing data. So you can create the model using the training data. After you create the model on the training data, now let's do the prediction on the validation set. And when we do the prediction on the validation set, we can get the value and check the value, check on the validation data, and then later on, after you get the best parameter, do the prediction on the testing set. So this is the prediction on the testing set. So you need to choose the best parameters. How to choose the best parameters? How to choose the best parameters? We can use the methods that we already learned before about the grid search. Okay, so I will show you later about the grid search. So we can do the performance measurement on the validation set. The performance on the validation set means we measure the accuracy, precision, recall, F1, and MCC based on the real value or the actual value of validation and the prediction value on the validation. The actual value on the validation, the prediction on validation with the weighted. The real value on validation, the prediction on validation with weighted. Okay, with the KNN, the result is very good. 1 means 100%. So it means this is perfect. The model can predict the data on the validation set 100% correct. So we can create models with different parameters when the performance is low. So last time we learned about the KNN. We can set up maybe if K equals to 3 is bad, we can change. Let's say K equals to 4. What about if K equals to 5? We can change the parameters. Since we get the best performance, then we can use this model for prediction. Because 1, 1, 1, 1, 1, everything is good. So we use this model for predicting on the testing set. Then we check on the testing set. We predict on the X test, we can get the prediction result. And again, we measure the accuracy between the prediction and the actual, between the prediction and the actual, between the prediction and actual, and so on. And we got this one. So this result shows that there's a slightly lower compared to the performance on validation result. Previously, we have 1, 1, 1, 1, 1. And now on the testing result, we have 0.9, 0.96, 0.96, 1, and 0.94. If we look at the gap between 1 and 0.96, okay, the gap is not that high. So we can say, okay, the model is just right. Because the difference between the model and the testing is not that high. You can do with the cross validation. Okay. I will not explain again. Last time we already learned the cross validation. If the cross validation, we set k equals to 5, then it means we will split the data into 5 times. Then for every time we look at the data, let's say this is the fault number 5 as the testing, the remaining data will be the training. And then we can get the accuracy for the split one. If this is the testing, the remaining can be the training, and we can get the accuracy. And so on. After we calculate all the accuracy, we can get the average accuracy. Then we do again. So I will just perform with the grid search cross validation. We split the data into 80-20. We split the X and Y into 80-20. And then we use KNN, we use the grid search, we use the k-fold. So in this case, I'm using a range. Do you know range? Range. So I'm going to loop from 1 until 10. It means I will do every numbers from 1, 2, 3, 4, 5, 6, 7, 8, 9. And I'm going to check that one on the k range. So later on the parameter of the n neighbors, it will be running from 1 until 9. And I'm going to check which n is the best. Then we can do with the CV. The stratify fold means I'm going to split into 5. And yeah, this CV is using the k-fold 5. And we are using the parameter grid. The parameter grid means this is from 1 until 9. We want to check which n neighbors is the best one. For the scoring, we will check the accuracy, the precision, the recall, F1, and the Matthew correlation coefficient. And then we do the grid search and check the best parameters. After we get the best parameters, so we calculate we do the prediction with the best estimator. When we do the prediction with the best estimator, we got the value of the prediction. And again, we check the performance. We check the accuracy, we check the precision, we check the recall, we check the F1, and we check the MCC. And this is the result. Okay. Okay, let's have a break. Okay, after the break, I will explain about the code.